Today, we are very happy to have Andrei Parnachev from Trinity College, Dublin, and he's going to tell us about stress tensor sector of conformal correlators. Over to you, Andrei.
Thank you very much, Abhijit. Thank you very much for having me. It's a real pleasure. So I'm going to give Blackboard, well, not Blackboard, the tablet talk. Hopefully it will be reasonably interactive. So, and you know, these days, since we are not in the same room, it's always a good idea to try to make things more interactive in some way. So please ask me questions at any point. I'll also try to make some pauses for questions, but even without that, please, you know, don't hesitate to ask me. I'm going to talk about conformal field theories. With a large central charge, where by central charge I mean the coefficient which appears in the two-point function of the stress tensor. And there is some index structure, so the coefficient that appears there is what I call CT. And of course, you know, most of what I'm going to say is going to be, well, the interesting part, what I'm going to say is going to concern CFTs in spacetime dimensions d greater than 2. But as an introduction, I'll actually start by reminding you what happens in the d equals 2 case. And you know, in the d equals 2 case, the situation is nice because there is Virasoro algebra, and in particular, one can ask a question: what is the contribution of Virasoro descendants to, let's say, 4-point functions? And the Virasoro descendants, let me just remind you, like the simplest, the nice one is the stress tensor itself. So this is L-2. And then the level 4 descendant is something like this: L-2 squared minus 3/2 L-1 squared, which is basically t squared plus this number times dt. And then at level 6, there are two operators. One is, again, there are some numbers which are not very important. So this is L-6.
Sorry, did you really mean L-1 square?
Yeah.
Oh.
But I did, sorry, no, L-4. I meant L-4. That's what I meant. Thank you.
And you meant two derivatives on t.
That's right. So the level 6 is -6 plus some number L-4, L-2 plus some number L-3 squared. And then the second operator has, again, L-6 plus dot dot dot. So difference of the second guy is that there is L-2 cubed. So now the difference between, one way to classify all these operators is by looking at the highest power of the stress tensor that appears in them. So in this operator, in T, there is just one power of stress tensor. In lambda, there are two powers of stress tensor. So this is a double trace operator. The way we call it is a double stress tensor operator. And this guy is a triple stress tensor operator. And you still need to add, so it's important that to make them quasi-primaries, you still need to add pieces which are linear in T here, and quadratic and linear in T here. now the OP coefficient for the, well, let's say we want to compute the OP coefficients of all these operators with the primary, and this can be easily computed. For example, let's say we have a primary of conformal weight H. Let's say we have phi and of conformal dimension H. Then the HHT.
Sorry, Andrei.
Yeah.
One question. So you say in order to make this quasi-primary, you need to add this. So this is the condition that this should be primary with respect to the global part, or what?
Yeah, the global part. Yeah.
I see. But why should one stress tensor mix with the two stress tensor?
Well,
under just the global part.
Yeah, that just follows from the P of the stress tensor. So basically, what you do is, well, one way to see this is to so basically this T squared is everything that appears in the OP of two stress tensors minus singular terms.
Okay.
And then you can compute the OP of this guy with the corresponding descendant of the stress tensor, and in order for it to vanish, you need to add this piece.
Okay.
So the OP coefficients of these guys, so the HHT is just delta. Well, actually, what I'm going to do in most of this talk, I'm going to normalize all of my stress tensors to 1. So in this case, so when you have usual canonical normalization of stress tensors, where the normalized to C, then the OPE is just H. The OP coefficient of this guy is just H. But if I normalize it to 1, I have to divide by square root of CT. And the OP coefficient of lambda with a given primary looks like H squared plus H over 5. There is some number divided by square root of 5 CT squared plus 22 CT. And I'm going to be interested in the situation where CT is much, much larger than 1, so I'll neglect this piece. So this basically is some number times H squared. Something like perfect with my pen. Plus
sorry, I missed what lambda was, please.
Lambda is this level 4 descendant of the identity.
Thank you.
Over CT. So basically, this H squared comes from T squared term here. So this H squared comes from T squared term here, and H over 5 comes from this dt. And then the story is that for a K stress tensor, try to make it slightly, for the K stress tensor, the leading, well, so for the K stress tensor, the OP coefficient HHT to the K behaves like, starts with H to the power K, there's some number, then there's some other number, H to the power K minus 1, and so on, plus some number times H, and all of this divides CT to the power K over 2.
Sorry, and the operator that multiplies this is O?
Operator that multiplies what, sorry?
Sorry, so sorry, this CHH, so when you take the lambda with O, you get an O with this coefficient.
Yes, that's correct.
And with the appropriate power downstairs. So if you take lambda, that would be whatever, 1 over ZQ. Or 1 over Z to the 4.
Yeah.
Okay.
That's right.
Okay. 1 over Z.
All right. So So these are the structure of the OP coefficients, and I guess so the main lesson is that the leading behavior of these OP coefficients is h to the k, and all these subleading terms come because you have to worry about these extra terms in the definition of your multi-stress tensor. Now, it's important that an interesting limit that we can take is the limit where h scales the same way as CT. So, and actually this is going to be the limit which I'm going to take throughout this talk. This is also going to be a limit which I'm going to take in high dimensional cases. So in this case, I will call the operator to be heavy. So heavy operator. H behaves like CT with mu, which is the ratio of H over CT constant, fixed. So there is a variety of reasons why this limit is interesting. One reason is because the holographic interpretation of a state created by such a heavy operator, well, in the two-dimensional case, it's basically a BTZ black hole. Let's look at the contribution of these operators to a 4-point function. So let's consider.
Sorry, Andrei, sorry to interrupt. So in the limit that you're considering, the operator is just literally t to the power k. All the mixing goes away. Is this right?
Correct. Yes. In this limit, all these higher order terms. Well, actually, it's not. Yeah. So it's not quite true. So and you'll see in a second what happens. But basically, what happens is in this limit, these high order terms in the OP coefficients are negligible compared to the leading term. So in this aspect, you're right.
Okay, and then I can understand the h to the power k by ct to the power k by just successive actions of the t's.
Yes, that's correct.
Okay, thank you.
So let me call. Let me consider a correlator with 2 heavy operators and 2 light operators. Where heavy operators have conformal dimension h, which is the order of CT. So let me put the capital H here. So and light operators have conformal dimension of the order 1. So now let's look at the contribution of a given K stress tensor operator to this correlator. So the OP coefficient, which comes here, scales like h to the power k over ct to the power k over 2. And the OP coefficient, which comes here, scales like h to the power k plus h to the power k plus 1 plus ... over ct to the power k over 2. So that's the product of 2 guys. So now,
sorry, I probably was spacing out, but what was L, please?
Oh, the L is a light operator.
Light operator. Okay, thank you.
Light operator whose conformal dimension is little h.
Is little h.
Now,
thank you.
So now the whole contribution is proportional to mu, which is the ratio of the heavy conformal dimension over CT. Something's really wrong with my pen. Never happened before. Something really new. Maybe it just needs, hopefully now it will work. Good. So I just needed to got a bit unscrewed the tip. So, okay, great. So now we have mu to the k. No, it's still not working. So now we have mu to the k. And then there is some non-trivial polynomial in h. There are some numbers in front of all this h. Plus hk minus 1 plus dot dot dot. Oh, okay, maybe now it will be working. So now the lesson from this is that the contribution of a k stress operator is proportional to mu to the k, and it contains all this data that comes from the oblique coefficient of the k stress tensor. So in other words, if you look at the 4-point function of two heavy operators and two light operators, expanded in powers of mu, this 4-point function will still know about all oblique coefficients of the multi-stress operators and your generic light primers. So in principle, you can, by computing this 4-point function, you can read off all oblique coefficients of multi-stress operators and generic primers.
Okay, so this is the sense in which you cannot throw away the subject.
Correct. Yes.
Because they are involving a light operator somewhere.
Yes, yes, correct.
Thank you.
So, in fact, in 2 dimensions, so if we are only talking about the contribution of multi-stress tensors, then this whole object is what is known as the Virasora vacuum Virasora block. So it's a contribution of all Virasora descendants of the identity to a heavy, heavy, light, light 4-point function. And it's actually known. It has been computed exactly. And it has a very simple form. So it's given by the exponential of delta times curly f, where curly f is the following function: minus log times sinh square root of 1 minus mu well, okay, so one way to write it, I mean, you can write it in terms of z and z bar, which is the standard coordinates. But I think in what I'm, in what I'm going to do, I'm going to consider the correlator where, so this 4-point function, it has, like all these operators have positions, and I'll consider a correlator on a cylinder. So this correlator on a cylinder of, so in 1 + 1 dimensions is just S1 cross R. And Z and Z bar are going to be e to the I delta t plus minus delta phi. Where well, t is time, Lorentzian time. If you want to consider Euclidean time, then obviously there will be no I in front of delta t, and phi is the coordinate on the circle. So in these coordinates then, and this is the same as delta x plus minus. So this is going to be a separation of my light operators. So what I'm going to do is I'm going to put my light operators somewhere in the middle of the cylinder. The separation in the x plus minus coordinates between the light operators I call delta x plus minus, and the heavy operators I'm going to put at plus and minus infinity. So in other words, what I'm computing here is I'm computing 2-point function of light operators in the background of heavy operators. So in this case, this f in these coordinates is just equal to square root of mu minus 1 over 2 times delta x plus. In terms of z coordinates, it's basically delta x plus is the same as log z. So we're going to have something like square root of mu minus 2 over 2 times log z. So this is what this function f is, okay? So it's been computed
Andrei?
yeah.
Sorry, what is delta in the exponent? e to the power delta.
H. Yeah, it should be H. It's going to become delta once we get into high-dimensional story. But for now, we're discussing 2 dimensions, so it's all holomorphic, among other things. So it only depends on X plus.
Okay. Okay, thank you.
Any other questions?
So in order to get these coefficients, you have to then expand this in blocks and so on.
Exactly. Yes.
Global conform blocks.
Right.
Okay.
So, in fact, let's do that. Well, instead of expanding it in global conformal blocks, let's first expand it in powers of mu. So, expanding this f, this curly f in powers of mu, we get the following. So, the first term is something which I call f2. The second term is mu squared times f2 squared plus f3. And I'll explain what f is in a second. f3, f1. The third term is mu cube times f2 cube plus f4, f2, f1 squared plus f3, f2, f1, and so on. So you see the pattern. So the other mu term is just f2. The other mu squared term is a product of all possible combination of 2 f2s such that the indices sum to 4. Other mu cube is product of all possible cubical terms such that the indices sum to 6, and so on, where the definition of fa is just 1 minus z to the power a hypergeometric to f1 a comma 2a 1 minus z.
So in mu cube there was f2, f2, f1 square.
F2, that's F3, I guess.
Oh, yeah. F2, F3. I see F3. Yes. Thank you.
Thank you. So,
Andrei, sorry.
Yeah.
How is it that this is only function of z and not z bar?
Well, it's all holomorphic, so it's all 2D.
Oh, okay.
We'll see in a second what's going to happen in the.
No, but even in 2D, you do expect. Okay, so these are chiral operators.
Yeah.
Okay, this H, all these heavies as well as light are chiral operators.
Yeah.
So you're just considering one sided thing.
Mm-hmm.
Yeah. Okay.
And if it is not chiral, you just get a product of the Z dependence with the product of the Z bar.
Correct.
Yeah. All right. Thank
you. So I must say that this structure is just an observation at this point. So it's not, it's a fact that it has a structure, but at this stage it's an observation. Now, so that's what happens in 2D. And
sorry, Andrei, sorry to interrupt. But the powers of mu tell you which of these operators is being exchanged, right?
Absolutely, but that's something I wanted to mention, that operators that contribute, for example, to this term, to mu squared term, involves t squared, and by t squared I mean schematically t squared, because this is really a lambda operator. Then t squared t d2t, and so on, t d4t. So all of these operators are going to contribute with their own OP coefficient. This is what I denoted by O6(1), I believe. So this is operator at level 8, and so on. So this
Could you flash again this expression for O6(1) that you had on the first page?
Yeah, so the point is that there is this is basically an object which has 2 t's and the second derivative.
Yeah, got it. Yeah, thank you.
But this tells you the lesson. So all of these OP coefficients are known. In 2D, everything is like computable, you can extract them, everything is known, everything is very nice. But the lesson is that to order mu squared term, there are infinitely many operators that contribute with more and more derivatives. To order mu cube term, there are also operators that contribute, infinite many operators, which are cubic in T with, again, infinite many derivatives. I mean, many derivatives. So that's the story. And so that's basically the introduction. So the 2D case has been known for a while. And the question that we are trying to ask is what happens in high dimensions? So the main question.
Sorry, I missed something here, Andrei.
Mm-hmm.
I thought that lambda would involve mu squared and that lambda was a very particular operator.
Yes. So lambda is a particular operator in the sense that it has dimension 4.
Okay. So then at dimension 6, there were two such primaries?
Dimension 6, there are 2 operators of dimension 6, but one of them has 3 T's and the other has 2 T's.
So the 2 T's does not contribute at this.
The one that has 3 T's contributes to order mu cube.
Yes.
The one that has 2 T's contributes to order mu square.
I see.
So another way to count these operators is not by their level, but instead by the number of T's that sits in them. And if you have, and that's what we are doing here. So in particular, all operators with 2 T's contribute to order mu square, but they can have as many derivatives as you want thrown in.
I see. And the factors of C also match, because the factors of C come from the number of T's, not from.
Correct. So that, yes. Absolutely, yes.
Yes. Okay, fine.
So one more question, Andrei, sorry. So this mu squared operators, there you have 2 T's and a bunch of derivatives. And those derivatives just are like, they just increase, right? The number of derivatives. So that's an infinity of operators. Right. But now for mu cube, you will have probably 2 infinities or something like that, because the derivatives can be sprinkled in multiple ways. And as you go to higher and higher powers of mu, you will the number of operators will proliferate very fast.
Correct.
Right, depending on how you can sprinkle derivatives inside.
Right.
Okay. And roughly speaking, how does the number of operators grow?
Well, you still need to. That's a good question, which we personally didn't have to worry about, because these operators all have the same conformal dimension and the same power of mu. So in the end, what we are going to be computing, if you wish, is the contribution of all these operators combined.
Okay.
So they have exactly the same quantum numbers, and we basically compute. They can combine contribution. But
why do you say
basically you need to impose the condition that they're primaries, or quasi-primaries in this case.
But why do you say they have same conformal dimension? As you sprinkle more and more derivatives, they will become higher and conformal dimension. Right?
Yeah. What I mean is, you can suppose you have 4 derivatives to throw in.
Yeah.
In principle, you can have different ways. Once
I see. At that level, it's the same.
It's fixed, but in principle, you have different ways of throwing in. So then
you will be working with the collection of those operators.
Yeah.
Wouldn't the number of operators just grow as the number of multi-particlings of
the number of what? Sorry.
Multi-particling, both symmetrizing K-stress tensors and descendants, and then removing the overall derivative.
So let's say, let me understand what you're trying to say. So if you look at this D4 term, like what would you say about that? So I would say that in principle, you can have something like this, and you can have something like this, naively.
Well, I would have thought for 2 T's, you don't have this kind of thing. You just have a single infinity.
Right. So you can think of it as all of these modulo things that are total derivatives.
Modular thing. Well, yeah, that's probably.
And the total derivative is 1 over 1 minus x. Just multiply the partition function of anything you can form with KTs and all derivatives, and then multiply that by 1 minus x, or 1 minus x squared.
Yeah. That sounds right. Yeah, that sounds right. But yeah, as I said, we don't have to in what I'm going to say, we don't have to worry about this.
Okay, good. Thanks.
Any other questions? All right. So, so the main question which we asked is what happens in high dimensions, and the reason, the reasons why we want to study this. Well, there are a variety of reasons. I don't know how much I'll be able to to discuss today, but one reason is, as you'll see in a second, the limit which is closest to 2D limit in high dimensions is a light cone limit. So light cone limit, which in our coordinates, well, let's say this corresponds to taking delta x minus to 0, keeping delta x plus fixed, which in the z coordinates, now z coordinates, corresponds to taking 1 minus z bar to 0, keeping z fixed. And in this limit, things simplify quite a bit. There's some interesting structure which emerges in the high dimensional correlators. And there is a hope also that there might be an algebra which stands behind the structure. So kind of questions that we want to ask is there some kind of algebra behind the correlators near light cone? So these are kind of questions. And the second reason is correlation to black hole physics. So as I mentioned, I'm actually going to explain this. So black hole. So in high dimensions, again, we define the same quantity mu, which is the ratio of conformal dimension of a heavy operator to the central charge. And this is actually going to be proportional to the mass of the black hole in the units of anti-de Sitter space. Black holes, of course, symptotical anti-de Sitter. And so then we can ask all sorts of questions. Most natural question is, does the heavy state thermalize? So if you have some heavy operator, and we probe it with light operators, are these responses going to be the same as the responses from a black hole? So is there thermalization? And then one can ask all sorts of other questions, in particular, like one, so thermalization. In particular, we spent some time trying to understand the very particular observable in the black holes, in asymptotical anti-de Sitter black holes, which is called the phase shift. So I'm probably not going to have any time to talk about the phase shift. So let me just mention it now. So this observable is nice because this is something. So generally, when you compute heavy light correlator in holographic CFTs, the contribution to these correlators comes from the stress tensor sector, which we just discussed, which are basically a bunch of stress tensors, but also there are multi-trace operators made out of external operators. And the story is basically that the stress tensor sector thermalizes, but these multi-trace operators are not going to thermalize. So if you're looking for some nice observables, these observables should be the ones that are insensitive to the multi-trace operators. And the phase shift turns out to be precisely such an observable. And of course, there is some other physics. There's all sorts of nice physics associated with this phase shift, because this is the object which is defined in the high energy scattering. And the kind of questions that you can ask is what happens when the scattering becomes non-elastic? That's the kind of questions that people studied in the 80s. Well, like people have been looking at them for a while, and there are some interesting lessons that you can learn. But I probably won't have any time to discuss it today, so I'm just mentioning it now.
So by multi-trace, do you mean like two heavy operators?
No, too light.
Two light operators, actually.
Yeah, the heavy operators decouple. Okay, so these are my motivations. Any questions? Okay, so let's now look at the heavy light correlator, and for simplicity, let's discuss D equals 4 case. Although everything I'm going to say is in principle, I mean, the situation in D equals 6 and any number of even dimensions is very similar. But let's just simplify our life. Discuss D equals 4. So the limit that we're going to consider is the Lightcon limit, where 1 minus z bar goes to 0. So in this case, again, we can compute.
I'm sorry, Andrei. Sorry,
Yeah.
just so in this second point, the correlator, that the scattering that you are obtaining, is it essentially scattering in classical general relativity?
Correct. Yes.
Sorry, one more question.
Hmm?
Sorry, once you've finished answering.
Well, go ahead.
The thing that when you took this limit of operator being heavy and stress tensor, central charge being heavy and the ratio fixed, the thing that bought you was to be able to work number of in sectors labeled by number of stress tensors. Is this right?
Correct.
Okay, thank you.
Well, also this allows you to compare CFT results and gravity results. Where by gravity results, I mean calculations which are done in the background of asymptotically ds black hole.
Yes. Okay. But from the point of view just of CFT, if you were just looking at CFT, it allows the separation, and also the block is only known in this limit, right?
Well, actually, the block is not really known. So in four dimensions, we don't really know the block. That's what.
I was talking about the 2D block. Even the 2D block is only known explicitly in this limit, right?
That's right.
Okay, thank you.
So yes, so it simplifies your life. It allows you to introduce this counting parameter, which is a number of the stress tensors, and it allows you. Yet you don't lose any data. You can recover all the big coefficients from this correlator.
Thank you.
Okay, so in this limit, the leading, and then we're going to again consider an expansion in powers of mu. So the leading term comes from the stress tensor. So heavy, light. So the leading term comes to stress tensor, so it involves mu times 1 minus z bar divided by 1 minus z to the power delta. 1 minus z bar to the power delta, where delta is now the conformal dimension of the light operator.
Sorry, Andrei, sir.
Yeah.
Sorry, but so is it a priori clear that the relevant limit that you should look at is the light cone limit, the 1 minus z bar going to 0, or is this just how do you know what is the limit that you want to look at?
Yeah, well, it's a good question. Yeah, well, I guess, yeah, I don't know. Like, there are in principle various answers to this question, but perhaps I'll use it as an opportunity to remind you that the leading contribution in the Lightcon limit comes from the operators of minimal twist. So that's basically the physics of this limit, if you want. So in particular, at each Yeah, so good. So it's actually a good point to have this discussion. So at each order in mu, where shall I write it? Let me write it here. So at each order, let's say at order mu, there is only one operator which contributes anyway. It's a stress tensor. And it has twist 2 and conformal dimension 4. So the contribution from it is given by this object. Okay. So there is this overall power. Then there is 1 minus z bar, which comes from the fact that it has twist 2. So 1 minus z bar is what we are sending to 0. And all high twist operators will have high powers. And there is a mu because it's a single stress tensor. And then there is this F3 quantity, which, remember the definition of F, it was this object. So this is basically the light cone limit of the conformal block of the stress tensor. Now, the next term is going to be mu squared times 1 minus z bar squared. So this is a statement that we're talking about twist 4 operators. Again, the denominator is the same. And here there's some function, which I call F2, I guess, plus dot, dot, dot. Well, actually, let me not call it anything, because you'll see in a second what this function is. Some function of delta and z. So, and then there is a term which involves mu cube and so on. Now, what's the role of this minimal twist condition? So at order mu, it doesn't buy you anything. But at order mu squared, I can have operators of the type where I have a bunch of derivatives, and these operate, all of these operators with infinitely many derivatives have twist 4. So these are direct analog of these operators in 2D, all double stress operators in 2D. So these are minimal twist, which is 4. And all of them are going to contribute here. So we need to, just like in 2D, we have to sum over all of these operators with the respective OP coefficients, and we get some function. However, we also have some other operators, which are also double stress tensors, but which no longer have minimal twist. So I can have boxes here. I can contract some of these derivatives. And these guys complicate your life because there are many of them. But this light cone limit allows us to throw them away.
You could also have operators where the indices of the stress tensor contract with each other.
Correct. So these are also high twists. So all of them we kill by taking the light cone limit. Okay, so that's what this operation does for you. And notice that, of course, the correlator by itself is still dominated by operators of the lowest twist. The stress tensor would still dominate the correlator if you take the light cone operator. Sorry, if you take the light cone limit, the usual light cone limit, then you have to throw all these guys away. However, the limit that we're going to take is a limit which keeps all of these operators, and that's a limit where mu tilde, which is equal to mu times 1 minus z bar, is fixed. So this corresponds to taking mu to infinity, and at the same time taking 1 minus z bar to 0. So in this case, all of these stress tensors, all of these minimal twist multi-stress tensor operators are retained, and this is the closest limit to what we observe in the 2D case. So this is the limit we're going to take. So in this case, it turns out that one can solve this correlator using a bootstrap approach if one is allowed to make a guess, an educated guess for it. And we're going to use the ansatz, which was very similar to 2D case. So ansatz. So we're going to assume that the heavy light correlator has the form e to the delta, just like it was in the 2D case, where f is given by mu times, well, mu tilde rather. Now the expansion parameter is going to be mu tilde times f3 plus mu tilde squared times f3 squared plus f, what is it, 4f2 plus f5 f1 plus mu tilde cube f3 cube plus f, say, 4, what is it? Now it has to be 9. F4, F1 plus dot, dot, dot. So you see, it's the same kind of ansatz that worked in the 2D case. Namely, here, all terms that are quadratic in F such that the subscripts sum up to 6. Here, all sorts of terms that are cubic in F such that the subscripts sum up to 9, and so on. And then we can do the bootstrap for it. Namely, we need to look at the cross channel, and the cross channel. So this was the so far when I was talking about the contribution of the stress tensors, multi-stress tensors, I was talking about the channel where I fused two heavy operators together and two light operators together, and multi-stress tensors propagated between. Now let me talk about the cross channel where I fuse heavy and light operators. Heavy light, and the operators that propagate here are operators of the type heavy light, and I can sprinkle a bunch of derivatives, and I can also sprinkle a bunch of boxes. So number of derivatives, let's say is L, and number of boxes, let's say is N. So number of derivatives, the number of uncontracted derivatives is basically a spin, and the number of contracted derivatives, number of boxes. So,
Andrei, sorry, just going back to the first channel where you exchanged two heavy merging. The operators that are traveling here seem to be basically in one-to-one correspondence with the 2D thing, right?
Yes.
Just all the derivatives are symmetrized, all the indices are symmetrized. So it's just like all having Z derivatives.
Correct.
Same number, basically. Thank you.
Yeah. So the conformal data here involves the OP coefficients and the corresponding OP coefficients, and the anomalous dimension, so the heavy light operator. So in order to reproduce the correct Z-bar behavior, the OP coefficients have to have this form. And by the subscript K, I mean the OP coefficient, the contribution of the coefficient that multiplies mu to the K. So this multiplies mu to the K. So there is L to the power K, and the anomalous dimensions of the form gamma n to the K, L to the power K. So now let me just give you a flavor how all of this thing is done. Let's take order mu result, or rather order mu tilde result. Let's take this result and expand it in powers of Z. And what I'm going to get in this case is something like, so if I take this, it's just a light cone block of the stress tensor, expanded in powers of Z. So what I'm going to get is something like some number plus some number times Z plus some number times Z squared plus dot 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 plus again the same kind of polynomial, well, not polynomial, same kind of series times log Z. So that's what happens if you just substitute the corresponding numbers. You just substitute a equals 3 in the hypergeometric function here. It's basically log times something plus, so it's basically some series plus some series times log. That's all there is. That's what F3 is. And now we need to match it to the to the cross-channel expansion. So in cross-channel expansion, the coefficients of the anomalous dimension are going to map to the coefficients which appear in front of the log. Well, that's kind of obvious. And the coefficients of these guys are going to map, well, they're going to enter both here and here.
I'm sorry, I'm losing it, Andrei. So these anomalous dimensions are anomalous dimensions of the
heavy light operators. These anomalous dimensions of heavy light L command.
Okay.
So these are anomalous dimensions in the cross channel.
Yes, thank you.
So the point is that by matching, well, maybe I should write, yeah, I don't know. It's like, I guess I'm a bit slow. So probably, in principle, I could write explicitly the heavy light block and tell you how the P's and the gammas appear in this kind of expansions. But let me not do it. And just perhaps you can believe me, that's true. And from matching, from matching the mu tilde F3, I can read off all the P's and all the gammas in the cross channel. Now, notice that if I'm interested, now let's go to the mu squared term, rather mu tilde squared term. So in the mu tilde squared term, again, I can expand. I only have 3 unknown coefficients in my ansatz. So I can expand my ansatz for mu squared term. And the interesting part of this ansatz is going to be the same kind of series times log squared z. So this term is entirely determined by the conformal data coming from here, because the log squared term comes from the square of, so basically the way these logs appear is you have something like z to the power delta, heavy light, and then it gets anomalous dimension, so it gets plus some gamma, and then you expand for small gamma, so it becomes at leading order gamma log z, but at subleading order it becomes gamma squared log squared z. So at order, so the mu squared term that multiplies log squared is completely determined by gamma 1. So I can completely fix this term from my order mu tilde result, and then I can read off these 3 coefficients and completely fix the answers. And then I just keep going. So at each time, at each point, yeah.
Sorry, here there was one equation, right? I mean, you also have terms with the log z and also with the thing without log z.
They're
so
actually
log square, log, and order 1. I mean, multiplying.
Yeah, they're actually infinitely many equations because you match all these coefficients. So you get more than one equation.
But then with this, the way you said it, you are just going to be able to fix the log square component, right?
Correct.
Oh, but you are saying once you fix that, you just, from there, the reading of 3 numbers is easy because you have.
That's right. That's right. All these 3 numbers are here. That's right.
So the idea is always to compare the top power of the log.
That's right.
The top power of the log is always the gamma 1.
Correct.
I see.
Of course, at next order, you can compare the top power of the log and the next power of the log. So basically, everything that doesn't involve the lowest power of the log is what's determined by the previous data.
Right.
And you have much more equations than you have undetermined coefficients. So,
but why do you even need why can't you? So is it that you cannot do just with the top power of the log? You need the next.
Yeah, I think at some point, actually, I don't remember details, but I think at some point you might need the next power because the number of coefficients also grows. But I'm not 100% certain.
Okay.
I'm sorry, I'm a bit lost here. So in the earlier expansion where you had this heavy going to light, you had this expansion organized by this power of mu times 1 minus z bar.
Yeah, it's mu tilde, yes.
And we understood what operators contributed there. Now, now when you're expanding here in this new channel, there's an infinite number of operators contributing. And which operators do you have to keep to reproduce any particular order in that expansion?
Yeah, so you have to keep all of them, but now the expansion in powers of mu tilde are the expansion of these coefficients. First of all, this behavior in L is fixed by the 1 minus z bar behavior. And well, sorry, so if you wish, let me talk about gamma. So gamma n comma L is given by gamma n 1 over L plus mu tilde squared. So there's mu tilde here, mu tilde squared, gamma n 2 over L squared plus dot dot dot.
Sorry, so N is the number of contracted derivatives and L is the number of uncontracted derivatives?
Correct, yes.
Okay, thank you. Okay, please go on. Yes.
Any other questions?
Sorry, I still didn't get it. So do you have to keep, what I didn't get is that, are you truncating on both sides? There's an infinite number of operators here. Which of them contributes to some power of 1 minus z bar?
Yeah. So on what we call the S channel on this side,
yes,
the heavy light side, infinitely many operators contribute. So the point is that the contribution comes from operators of very high spin.
I see. So what you can do is then get asymptotic behaviors of gamma.
Correct. The asymptotic behavior is this. So as you see, the asymptotic behavior is 1 over L here and 1 over L squared here. So you may ask, where did this come from? And this came from the 1 minus z bar behavior that you know from the other side.
I understand. Now
so when you integrate different powers of L, you basically get the correct power in 1 minus z bar.
So this is some variant of the usual story that a few operators on one side are asymptotic behavior on the other.
Oh yeah, of course. Yeah.
Thank you.
There's nothing fundamentally new here. Yeah. Another question.
But Andrei, then this guess is very important, right? That the guess allowed you to parameterize everything in terms of very small number of coefficients.
Right. Correct.
Okay.
Sorry, I missed that even. What was the guess, please?
The ansatz that we used.
And could you show that again, please? The ansatz.
So it's this.
Oh, and that you hadn't proved.
No.
That was just on one side, right? This was on the heavy light side, right?
Well, it's the full correlator. So
right, I understand. But you could prove it by expanding on that side, couldn't you?
Well,
at least for the first few terms, you could, right?
No, yeah, of course, yeah. I mean,
okay, thank you. Yeah.
So let me now make a few comments about this. So first of all,
in particular, Andrei, this ansatz also means that the coefficients of the multi-stress tensor guys are some analytic functions of number of derivatives. That's why you are able to parameterize it as just this function, right? A small.
I think that's right. Yeah.
If it were not analytic, then there is no correlation between the two. Then there's no reason why it should sum to nice function, right?
That's right. But regarding the synalticity, let me get back to the synalticity.
Okay. Okay.
It's going to be slightly different on the synalticity issue, but
I see. Okay.
Yeah. Sorry. One question about that. It seemed to me that in this limit on the heavy light side, the whole structure was very near to the two-dimensional theory.
Oh yeah.
For some dimensions being different.
Right.
And I was wondering whether that was the reason that this nice structure is working.
That I'll also mention. Let me make a bunch of comments now.
Yeah, thank you.
Let me analyze this whole result. So the first comment is that, this way we compute the full correlator, but it turns out, as I mentioned to you, this full correlator actually has this form. where f has a finite limit. So these coefficients, by the way, that appear in front of f3, f4, f2, the coefficients that appear are now delta dependent. So it's a big difference between the 2 dimensions and the 4 dimensions. So all these coefficients are going to be delta dependent now. So the coefficients that appear in f are going to be delta dependent, but it has a finite limit as delta goes to infinity. And this limit actually is something that you can compare with holography. So in holography, of course, the delta goes to infinity limit. In delta goes to infinity limit, this correlator is dominated by the Wilson line. So you can compute this Wilson line and recover this function f. And this computation, so you need to be a bit careful because we are dealing with, you have to throw away all these non-minimal twist operators. So you have to do some rescaling of the metric and play with it a little bit. But in the end, it's a doable exercise. And it turns out that this f you can compute. So in 2D, remember, it was just some log sinh. In high dimensions, it involves some, there's an explicit formula for it. So Wilson line produces this f with delta equals infinity. It's basically some elliptic integrals, f1 Apple functions in terms of. And then you can compare. No, you can compare the gravity and the Wilson line calculation and the delta equals infinity limit of the bootstrap procedure that I just discussed, and the two sides perfectly agree. But the good thing about the gravity result is that it gives you closed form expression. So the second comment is that
Andrei,
yeah.
How do you get 1 over delta corrections from gravity?
Oh, you don't. Yeah, that you don't know how to get. So, sorry. That's from Wilson line. You don't get it, but in principle you can get the full opaque. That's exactly what I was going to talk about now. So from the Wilson line calculation, you only get the behavior of f as delta goes to infinity, as I said. But in principle, you can get all these opaque coefficients from a gravity calculation by just computing a 2-point function of scalars in the background of a black hole. Perhaps I will very quickly remind you. Well, yes. So what you do is you have, as I said, mu is basically the mass of the black hole in the ADS units. And what you do is there's some black hole, you compute some gravity calculation, and you can read off this opaque coefficient. It's a bit hard, but it's doable. And an interesting fact is that for the leading twist operators, the leading twist multistress tensors, these opaque coefficients are universal. They do not depend on high derivative terms in your gravity Lagrangian. With respect to high derivative terms, bulk high derivative terms.
In what limit was this true again? Leading what?
Leading twist, minimal twist. So like everything I just discussed involved taking this final limit where we take 1 minus bar to 0 and mu to infinity, such mu tilde is fixed. So we take a slight limit, large mass. So this way we isolate all the minimal twist multistress tensors. So and these opaque coefficients, as it turns out from the gravity calculation, are universal in the sense that if you consider different gravity theories, like you add a Gauss-Bonnet term, let's say, to your bulk Lagrangian, compute these opaque coefficients, they don't depend on the Gauss-Bonnet term.
I see.
However, for non-leading multistress tensor operators, they will be dependent. So they are not universal in this respect.
So now adding a Gauss-Bonnet term would change the background Schwarzschild metric.
Correct.
So even though it changes the background, it doesn't change.
Correct.
Okay, so it's somehow the answer depends on very little information about the background.
Right, and that's of course what you see from the ansatz. So this ansatz works in any gravitational theory that you write down. So there is some rigidity to it. I must say that like the ansatz can be modified to deal with the subleading twist operators as well, this has been done and it all works. But like, let's not get into this. So you can actually make some progress in that direction as well if you're interested. But you lose some universality.
Sorry, Andrei, do you have some intuitive explanation about the point number 2? Why is it that it is inversal?
Good. So again, I can say a few things. So one is that this corresponds to this. So the big coefficients, the leading twist. So good. So this is the closest analog of 2D CFT that you can have in high dimensions. And the natural questions, and so one thing that you can, well, I already said that the ansatz seems to be rigid and seems to hold. You can ask, okay, why does it hold this ansatz? And one possibility is that there is some algebra, some analog of, I don't know how analogous it is, but some analog of the Virasoro algebra, which governs this correlator near a light cone. So algebra behind this. Let me mention a few things here. One thing to mention is that this object here, the light cone light cone limit of the stress tensor block is actually the leading. So the algebra here, if it's anything, it's very close to W3. So in particular, you can compute the character of the W3 algebra, and what you observe is that the leading term is going to be exactly like this, exactly mu tilde times of 3. And the subleading term is going to have exactly the same form. In other words, the character of the W3 algebra is actually going to have to satisfy our ansatz, but the coefficients are going to be different. So whatever you get from, whatever you compute in this near light cone correlator has the same form as a W3 character, but it's not quite that. In fact, have been a bunch of papers recently where people observed that how to get, well, the fact that this F3 appears from the, you can easily see that that's F3, the leading term, appears from the central extension of the W3 algebra, which is different from Virasoro. And the question is, is there some kind of algebra which has same central extension? And recently there were some papers where people basically looked at the ANEC operators, and these ANEC operators do seem to have this central extension that is needed for this leading term. However, at the moment there is no algebra. Well, so these ANEC operators are natural suspects. However, at the moment we don't know if there is an algebra which is behind all of this, but there are lots of indications that there is. So that's one of the reasons why this near light cone limit is interesting. Other questions? How much time do I actually have?
We are usually a bit flexible with the time because we had so many questions during the talk. It's fine.
Well, okay.
So you can, yeah.
Well, okay. Let me do this. I guess I wanted to make a few more comments about this result. So let me make a few more comments, the comments that I wanted to make. And then like there was some other part of my talk which had to do with thermalization at weak coupling, but let me not talk about that. Let me just focus on this part today.
Okay. Okay, great.
So that was the algebra story. I guess next comment that I wanted to make. So recall that mu, which is delta heavy over Ct. So this we can write as delta heavy over, let's say, R d times Rd over Ct. So
Andrei, sorry,
yeah.
just to understand this, universality a little bit. So, does it also mean that if one were to do a scattering experiment with the 2 gravitons going to 2 gravitons,
yeah,
and look at the amplitude in the light cone limit,
yeah,
then somehow it should be universal. It should not depend on higher derivative corrections to gravity.
Absolutely, yeah. Well, that one. That's a separate interesting story. So, which is actually it is closely related to what I'm talking about. That's the part of the phase shift that I didn't discuss, because the interesting limit that you take there is a Regge limit. And the leading term in this Regge limit, well, the leading term in 1 over n is dominated by stress tensor exchange. So you may ask a question, how do these multi-stress tensors appear? So they're basically in the usual graviton-graviton scattering, they're one-one suppressed. But if you scatter graviton off a black hole, they're enhanced. So all of them will contribute. So you can ask, you can study this question, and basically this is directly related to this heavy light correlator that I'm talking about here.
Okay.
So yeah, you will actually see that the high derivative terms do not affect. Well, the question is, can you isolate the minimal twist operators? So there's no, from the point of view of scattering, it's not a very natural thing to do to isolate minimal twist operators. That's the problem. So
no, if you take a particular limit, it's not that they will only those contribute.
Well, in the light cone limit, yeah, in the light cone, correct, good, right. So now, thank you for reminding me. So there, the relevant quantity is the impact parameter, and this impact parameter you can vary between basically, yeah. So you can go to the light cone limit there, and indeed in that limit there's only leading twist operators that contribute. Correct.
Okay.
Yeah, there actually, yeah. Now I was writing this mu, so this is just, so delta H over RD is delta H over R, which is the energy of the state, times divided by RD minus 1, which is the size of the d minus 1 dimensional sphere. Remember, we're in a cylinder. So this is just the energy density times RD divided by Ct. So in holography, the energy density, the energy density is, there is some number which in some cases is equal to 3/4 but times something, but in some other cases it's something else. But the point is the energy density is proportional to Ct, and then it's proportional to t to the 4th. Well, actually, it should be 4. I'm talking about t equals 4. So this is nothing but some number times t to the 4 times r to the 4th. So that's what mu is in 4 dimensions. And now the kind of expansion that we have of this correlator is the expansion. The expansion has the following form. It has mu times 1 minus z, 1 minus z bar, and then let's consider the planar limit. So planar limit, well, the large volume limit. So this is a limit where the sphere becomes, basically R3. So R goes to infinity. So in this limit, both Z and Z bar go to 1. So in particular, in this limit, 1 minus Z bar and 1 minus Z both behave like X over R, where X is the separation between the two insertions of light operators, bit in time and space. For this argument, it doesn't matter. So in this limit, all the hypergeometric functions collapse to 1. And the leading behavior comes from this factor of 1 minus Z cubed. So this is the kind of expansion parameter in the large volume limit. And now if you substitute mu, which is t to the fourth r to the fourth, and you substitute this, so the factors of r cancel, which of course what you should expect in the large volume limit. You should things shouldn't depend on r. And the expansion parameter is mu times delta x minus times delta x plus cubed. So this is the expansion parameter when you take the large volume limit and the light cone limit as well. Sorry, this is t. This is supposed to be t to the fourth. So that's a natural expansion. So if you consider generic correlator at finite temperature, the expansion is in powers of t to the fourth, and then it has to have delta x to the fourth. So the kind of terms that are allowed are delta x minus times delta x plus cube plus delta x minus delta x plus both squared plus dot dot dot. So if you take the finite temperature expansion and at the same time the light cone limit, all these terms disappear, and basically you have one function. So this light cone finite temperature correlator is a single function, and in holography, as I mentioned, this function is at large delta. You can compute this function. This is some stuff related to Apple functions. Generally, it's an interesting question what this function is for generic theory. But we don't believe that for generic large C CFT, everything is universal. Things will start depending on delta. Well, I guess that's probably all I really wanted to say. Let me just mention, since I started talking about what happens at weak coupling, let me just mention that you can ask a question: what happens in the simplest theory at weak coupling you can think of, free theory of, let's say, a joint scalar, so that you have large CT. And in free theory, of course, you can compute these correlators, light correlators, light heavy correlators, and you can decompose them in conformal blocks and so on. You can do a lot of stuff. So what happens in free theory is that. So remember that I mentioned that the stress tensor operators all thermalize at large CT. Actually, in 2D, this follows. In 2D, people showed that because it follows basically from the word identity of the stress tensors with heavy operators. But in high dimensions, it turns out that the stress tensor sector, all these multi-stress tensor operators do thermalize, be it at weak coupling or at strong coupling. So interestingly enough, they do thermalize. The crucial difference of the weak coupling theory, say, zero coupling theory, is that you have other light operators which will contribute, like trace phi squared, for example. And these operators won't thermalize. So there is a sector, large sector of light operators which will complicate your life. But as you increase your coupling, or suppose there is some marginal line, as you increase your coupling, presumably all of these operators get lifted and get decoupled, and then you end up with a holographic constant. So that's the kind of picture that we expect. So I guess that's it. That's all I wanted to say. Thank you.
Well, thank you very much, Andrei, for a wonderful talk. Let's all unmute and thank Andrei. Questions?
Could I ask a question which is maybe a bit vague? You were computing these heavy, light correlators. Now, and maybe this is what you were saying through parts of your talk, but as you indicated many times, the heavy operators, what they're doing is creating a black hole type background. So you might think that the same physics that's there in a heavy light correlator would also be there in a 2-point function of 2 light operators, just at finite temperature. Is that right? And can you use that to?
Yeah. That's well, good. So I actually forgot to mention one thing. I guess I just forgot it. So that question is perfect for it gives me an excellent opportunity. So when we are computing the heavy light correlator, the operators that contribute here are the multi-stress tensors. But another set of operators is the operators made out of, let me call the light gauge O's. So then there are like operators of this type. And then you can, of course, dress them with multi-stress tensors as well, like this.
We can't see your screen. If you're writing.
Oh, sorry, let me show. So it's not
no,
shared?
Well, no, I think the screen is visible, but what you're writing is not being updated. You see the diagram that you just drew, just one. Now it's
coming.
Yeah.
Can you see it now?
There's a lag. Yeah, there is a lag.
Okay. Sorry. So there are the stress tensors, and there are these multi-stress operators. Now. The OPE coefficients, I should have written down these OPE coefficients of multi-stress tensors. But basically, if you consider, let's say, the double stress tensor OPE coefficient, it has a form, let's say, delta minus, it has some kind of denominator of the type delta minus 2. And then there can be other integers. So it has a pole when delta is equal to 2. And the reason it has a pole is because the same kind of pole, well, at least we believe that the following picture is true. The OP coefficients of O's with multi-stress tensors are fixed, but the OP coefficients are fixed by the near boundary physics in IDS. But to get OP coefficients with multi-stress tensors, to get OP coefficients of O's, well, with these guys is a slightly harder exercise. I think the picture is that, so from the stress tensor, so you can ask a question, what happens when delta becomes integer? So there's a mixing of operators. So your multi-stress tensor has dimension, let's say 4, but at the same time, the double trace operator made out of O also has dimension 4, roughly speaking. Well, it's not 4, it's 8. I mean, so you have, say, double stress tensor at dimension 8, 2 stress tensors, and at the same time, you have if you have integer dimension, then operator made out of O's also have the same dimension. So they mix. And
sorry, Andrei, but aren't these subleading in twist?
No, they don't have to be, because the twist of double. Well, let's discuss the double stress tensor. So the twist of TT is. So that's twist 4 operator.
Yeah.
So it's dimension 8 and twist 4. Well, actually, yeah. So okay. So it's a good point. So the mixing here happens with. So if you're talking about this, So let's discuss a situation where there is a pole like this. So this mixing happens. This mixing happens with this guy. So this is not a minimal twist operator. But I think if you go sufficiently high, I think this physics that I'm trying to talk about now is not, no, and the physics of minimal twists are separate. So in other words, you can go to sufficiently high mu, and there will be mixing between minimal twist and the multi-trace operators made out of external operators. So I think this mixing happens. But just to illustrate it, the best example which I'm aware of for a variety of reasons, well, the example that I was thinking about recently is the example which doesn't involve the minimal twist stress tensor. Although, no, as I'm saying, it's not, I don't think a twist is relevant here. So the mixing is between this guy and this guy, well, and this guy. So this guy has delta -4 in the denominator, and this other guy has also delta -4. And then on top of it, there is something like this. So then what it produces for you, it produces some log. So this mixing produces some log. So that's interesting for a variety of reasons. But I guess one thing that I want to say is that the stress tensor sector thermalizes, and we know like this whole ansatz computes its contribution. But once you're outside of the stress tensor sector, once you talk about other operators, I don't think they necessarily thermalize. So the full correlator is not going to necessarily be the same.
So that means that you take two very heavy operators and you compute the correlator, too heavy and too light. That's going to be significantly different from just putting this at finite temperature.
Generally, yes. However, there are observables which are insensitive to, there are ways to zoom in onto the stress tensor sector. So one way is to just take delta to be large, the external delta. In this case, your light operators sort of also become heavy. The light multistress, these operators also become sufficiently heavy. And then the main contribution comes from the stress tensors, which are light. So that's one way. But depending on what you want, it may be an interesting way or a boring way. And the second way is to look at, as I mentioned, this observable that you get when you consider Regge scattering in the black hole background. The relevant quantity there is the phase shift, because Regge scattering is basically completely determined by the phase shift of the amplitude. So that phase shift, amazingly enough, isn't sensitive to the contribution of these guys. It's only sensitive to multi-stress tensors. That's why it's so nice. So one thing you can do is to take that object, and that's only going to be sensitive to multi-stress tensors.
Sorry, why is it another way taking the light cone limit, the way you did it just now? I mean, in the talk, where you scale mu and 1 minus z such that the product is fixed. There also, you don't get any contributions from OOT, right? You just get contributions from T, minimal twist in the multi-stress tensor kind of a thing. So that also is a way, right, to zoom into that.
Yeah, but no, that involves, so the phase shift depends on the impact parameter. So basically how you shoot your, it's Regge limit, so your geodesic is null. It's basically calculation that involves studying null geodesics in black hole background. But it still depends on where you shoot your geodesic. And if you shoot your geodesic far from the black hole, that's a light cone limit. So that one only depends on the leading twist multi-stress tensors. However, you can choose to, and actually for a variety of reasons, it's much more interesting to shoot it closer to a black hole, because eventually it will fall into a black hole. And then your phase shift actually will become imaginary, and you will probe inelastic scattering. But that physics depends on well, no, knows about operators which are no longer minimal twist, not about all operators.
But still stress tensor.
Sorry, just coming back to something you said. I mean, from the point of view of gravity, you take some very heavy state and you wait. You just expect it to thermalize, right? Completely. You would expect that you take any state of high enough dimension and you wait a little while and you get results that are basically indistinguishable from that of a black hole of the same mass. Isn't that correct? At least at sufficiently high interaction. Or how could it not work in an interacting CFT?
Yeah. I guess. I guess the problem here is well, here's the problem. So just technically getting this OBE coefficients for, let's say, double stress tensors is a bit, it's technically more difficult than getting them for the, getting the OBE coefficients between O's and multi-trace operators made out of O's in gravity. It's technically more difficult than getting the OBE coefficients between O's and let's say T to the K. So it's slightly, so it's just technically, no, unfortunately, I don't have a formula in front of me.
Yeah.
However, I think it's true that these OBE coefficients will depend on mu. Like if you believe, so suppose you do this black hole calculation, then you extract OBE coefficients, they will have some mu dependence. It's similar to the way, if you go back to the usual Witten diagram, where you have scattering of two light operators, that Witten diagram is decomposed, and let's say a graviton exchange. That Witten diagram is decomposed in terms of conformal blocks into the stress tensor conformal blocks plus conformal blocks of the double trace operators made out of external guys. And then you can ask, what happened with OBE coefficients? And the OBE coefficients are fixed. The OBE coefficients of, let's say you have O1, O1, O2, O2. So the OBE coefficients of O1, O1, and O2, O2 is completely fixed in terms of the OBE coefficients of the graviton. So because the Witten diagram, you know the answer. So that's how it works there. But in this case, the OBE coefficients of the light operators, well, actually, yeah. So yeah, you say this OBE coefficients will have some mu dependence, some non-trivial mu dependence. But maybe all of this mu dependence, what you really get is a product of the light, double, trace, heavy OBE coefficients. So some mu dependence, maybe all this mu dependence comes from the heavy, double, trace light.
I
Yeah, maybe you're right. Anyway, so yeah, I don't think I know the answer. But what you're saying is obviously like natural. So maybe you're right.
Maybe I can say one more quick thing. What's special about black holes and Einstein gravity is that only the metric is turned on. Right. So that would be the statement that the only operators that have non-trivial one-point functions are the stress tensor and its multitraces and derivatives and so on.
Yeah.
If we were in string theory, if we were going away from Einstein gravity, all operators would probably have one-point functions.
Yeah, yeah.
And maybe that's what causes the complications.
Oh no. That is certainly true. As I mentioned, if you do it in free theory of this exercise, you see with your own eyes how all these light operators don't thermalize. So that in free theory, you just see that happens. And generally at finite lambda, I think that will also happen. But yeah, I think, no, you're probably right. That at infinite lambda, probably the whole thing is thermal. Yeah. Probably right.
Okay.
So you basically, one just needs to compute this other B coefficients and that's it. But the part of the problem is, there's nothing to compare them with. So when you say something thermalizes, you need to be able to compute independently the heavy, let's say, O B coefficient. And how do you compute it independently if you only have gravity? So in gravity, you can only compute it from basically your black hole computation. So you already assume thermalization. So we have, like, for the stress tensor, we have the ansatz. Then we have the free theory, where we can compute them and observe that the living behavior is actually exactly the same. So that's another interesting fact. So in free theory, this leading delta to the k over ct to the k over 2 term in the B coefficient is the same as in gravity. And that actually is a consequence of thermalization of the stress tensor sector. So there are a variety of ways you can compare. But what do you compare it with in gravity? That's the problem. You don't have an independent calculation of the heavy OO B coefficient. That's basically the issue.
Okay, thank you.
One question, Andrei. So this ansatz that you wrote down for the minimal twist case, the correlation function of heavy light, can you kind of motivate it from some kind of ladder diagram where you get exponentiated form naturally?
Well, you mean it looks like econo?
Yes.
Yeah. No, unfortunately not. At least I don't know. So yeah, I don't know. Even in 2D, it's not so easy. I mean, these are different things. So yeah, I don't know the answer to the question, unfortunately. I wish I knew how to motivate this answers.
So perhaps related, you talked about in 4D how to work in this channel of heavy going to light, and then you re-expanded in the other channel of heavy light to heavy light. And all this has been done in 2D, and anything, it doesn't.
Oh, of course.
Yes. And does anything interesting come out there? Or it's just all trivial there?
Well, no, I don't think there is anything. I don't think there is anything particularly interesting that happens in 2D. Okay. But perhaps one thing I should mention is also it's an interesting connection. Is these anomalous dimensions in the cross channel are, of course, energies of, you can interpret them as energies of excited states in and there's actually separate calculations that you can do to sort of match all of this. It's not directly related to a question, but it's vaguely related. So
it's like the energies of light excitations in a black hole background.
Correct. So what you do is you start with a light excitation in ADS. These are all this generalization of like YLMs basically, and then you add a black hole, and you can treat the black hole as a perturbation. So mu in this black hole, let's say, is a perturbation parameter. So you can compute the correction to these levels, order by order and mu. And what you get is precisely this anomalous dimensions. So that's one physical way of interpreting this gas.
And you can do this also in 2 dimensions? Is there something?
Yeah.
And there's some non-trivial calculation there.
I think in 2D it's probably very trivial.
It's trivial. Okay.
And 2D, I think it's all, it's very nice because it's like, it's always good to go to 2D and see what happens there to check, but I don't know. Obviously 4D is hard.
Right. Thank you.
Any more questions?
Sorry, and this calculation works because you're at large angular momentum, and so the light stuff is far away from the black hole. The black hole is a small perturbation because you're not near its event horizon.
Well, you can compute. Well, good. So that's another separate interesting question. So you can ask a question: what's the radius of convergence? So suppose you have this mu. You always get some series in mu. Yeah, you can assume that mu is small and then get some series. And you can ask a question: what's the radius of convergence of the series? And that depends on the question. So in particular, as I mentioned, if you study scattering, like throwing these null geodesics, so suppose you fix the impact parameter, and then you grow mu. So eventually, this guy is going to fall into the black hole. Well, actually, it touches the photosphere. And that's precisely where the series develops some branch cut, basically. And but you can analytically continue it and get get the absorption of your. So your phase shift becomes imaginary. You can compute the absorption cross section, but this absorption cross section is just the usual geometric cross section short. So it's not terribly exciting.
Yeah, but for gamma NLs, you need L to, if L is large enough, the stuff is far from the black hole, and so
that's right. Right. So yeah, it's basically this input parameter is translated into well, yeah. So it's translated into L, if you wish, into little L.
Okay, thank you.
Okay, if there are no further questions, let's thank Andrei again for a wonderful talk and entertaining all the questions.
Well, thank you very much for all the questions.
Thank you very much for the excellent.
Thanks, bye.
Bye.